Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 22. Today we will explore other interesting topics in bipolar circuit design and amplifier design. But before we go there, I would like to refresh your memory about what we covered last time. All right. Last time we spent some time on two important concepts. The concept of input impedance and output impedance. And what we observed was the following. If we have a simple common emitter stage and we connect a microphone to it, of course with bias voltages and everything else, which I have not shown here, and if the microphone itself is not an ideal voltage source, but has some internal resistance as modeled by this Rm, then what happens is that we attenuate the microphone signal as we go from here to here. This attenuation arises because we have Rm here and we have Rpi here. If Rm is not under our control, meaning this is a microphone that we buy, then the only way to reduce this attenuation is to maximize Rpi. And that brought us to the concept of input impedance or input resistance. In this case, we would like the input resistance to be as high as possible so that the attenuation from here to here is minimal. You can see that if Rpi is infinity, meaning it's an open circuit, then there is no attenuation from here to here because Rm carries no current. Now, we also saw that if our common emitter stage tries to drive a load, such as a speaker, then it loses gain. We saw that, for example, if RC is 1 kilo ohm and we connect it to an 8 ohm speaker, then suddenly the gain drops to less than 1. And to understand that, we modeled the common emitter stage along with the input signal by a Thevenin equivalent, of course only for small signal analysis. And we said there's a voltage source here, which is equal to minus GM RC times Vin. That is the voltage gain that we would have, voltage that we would have from here to here before we connect to the load. And then once we connect to the load, we have the load resistance attached to the output. And this tells us that we have an attenuation between the Thevenin resistance of this amplifier and the speaker impedance. So that brought us to the concept of the output impedance, which is really the same as the Thevenin impedance. And from those, we realized that the input impedance of a simple common emitter stage is equal to Rpi. The output impedance is equal to Rc, if you want to be more precise, Rc in parallel with Ro of the transistor, because they both are connected between the collector and ground, AC ground. And of course the voltage gain is minus GM RC. So today we will look a little more closely at these concepts and incorporate them in another interesting topic, which is what we call cascaded stages. So we're going to look at cascaded stages, cascaded amplifiers. Then we look at the problem of gain variation in the common emitter stage. And as a remedy to that gain variation, we will introduce a slightly different topology, which we call the common emitter stage with emitter degeneration. All right, so let's begin with cascaded stages. And this is relatively natural to ask if we build one common emitter stage and given various constraints, its gain is not sufficient. So for example, I would like to have a gain of 50 from here to here, but the amplifier can only provide a gain of 20. Then what do I do? I have done my best to maximize the gain of the stage, this amplifying stage, but it was not possible to achieve a gain more than 20. Well, what we are thinking is maybe we can place another stage after this stage, meaning that we amplify the signal from here to here, and then we give it to another stage, we amplify it further. So the overall gain should be higher than what we have in one stage. And that's what we call cascaded stages. The word cascade should not be confused with the word cascode, which we will study towards the end of this course. These are completely different things. So in an abstract level, this is what we are thinking. We have one amplifier, input, output. It has some gain, so we call it A1 maybe. And then we have another amplifier that we place right after this one. So we call that A2. And what we are hoping is that if we start from the input of the first amplifier, amplify the signal here, and amplify signal more here, then hopefully we have a higher gain from V in to V out. Okay, so that's the objective. All right, so we know one topology that can serve as an amplifier. So we're going to use that topology here and here. We start out with a common emitter stage with one transistor. We have a resistor here, we call it RC1. A transistor here, we call it Q1. This input, of course, would need a bias voltage, if you remember from the past, some sort of battery, and then we have something in series with the battery, like a microphone. I will just neglect, I will ignore all of that. I'll just call this V in. With the understanding that there is a bias current, there is a bias voltage, there is a bias voltage here, supply voltage here, all of that, we just don't worry about them. All right, now, if the gain from here to here, meaning associated with the stage, is not enough, maybe what we can do is give this signal to another common emitter stage with another load resistor, which we call RC2. This guy also needs a battery supply voltage, so we'll just share their supplies. We call this VCC. Again, remember that these are all little shorthands that we are using. What we mean is that there's a battery from here to here. These are all connected as ground. These are all connected as VCC, and there's a battery between them. Again, for simplicity, we don't draw all of that. And then the output is taken from the collector of the second transistor. We call that V out, and this is called Q2. So we see the correspondence between these stages. This is called a two-stage amplifier. Sometimes we might call it cascaded amplifiers or cascaded stages. All right, so what we would like to find now is the voltage gain of this cascade from here to here. V out over V in. How much is the gain? So you might see this language that I'm using. Sometimes I say the gain from here to here. And by that we mean if the signal starts from here and ends up here, how much gain does it experience? Of course, the exact expression would be the output small signal value divided by the input small signal value. All right, how do we go about calculating the voltage gain? Well, we could draw the small signal model of this entire circuit, replace each of these devices with its corresponding small signal model, and then just write equations. That's not that hard. But can we, if you are lazy, can we take some shortcuts so that we don't have to do all of that? Maybe we can simplify things. So let's make some observations and see. All right, so let me change the color of my pen, and I'll make the first observation here. If I call this node X, the collector of Q1, what I can say is the following. We have some gain from V in to X. We call that Vx over V in. And then we have some gain from X to V out. We call that V out over Vx. And what we can recognize is that the gain that we are looking for, V out over V in, is just equal to Vx over V in times V out over Vx. So this says, to find the overall gain, all you need to do is find the gain of this guy, find the gain of this guy, and multiply. So that's one simplification. All right, so we will call this gain AV1 and this one AV2. And our objective is to find AV1 and AV2. Knowing that the small signal gain of a simple common emitter stage is equal to minus GM of the amplifying device multiplied by the total resistance that we see between the collector and AC ground. Okay, is AV1 in the circuit equal to minus GM1 times RC1? Is that correct or is that not correct? Well, it's not correct. This is because at this point, at the collector, the total resistance tied to ground is not just RC1. We have RC1 going this way to AC ground, again building the small signal model in our head. But then going this way, we have something. There is something attached from here to AC ground. And that something is R pi. So the total resistance seen at this collector is not equal to RC1. Now, if that's a little confusing, we can go ahead and draw a bit of the small signal model just to visualize these. So let's do that. Here's what we'll do. We'll just draw the first stage in its original form. We don't bother with the small signal model here. But for the second stage, we draw the small signal model, like so. And this is R pi 2 to distinguish it from R pi 1. This is the small signal model of the second transistor. This is V pi 2. And then this current source here is GM2 V pi 2. And then this resistor is RC2. And this is the output. This is node X. And as usual, I'm assuming the early voltage is infinite. Okay, so similarly here, I'm assuming that the early voltage is infinite, just to avoid any confusion. All right, so then here, if I'm trying to find the small signal gain of the first stage, it's not that hard to see. I say the gain is equal to minus GM of the amplifying device, GM1, times the total resistance that is tied between the collector and AC ground. So going this way, I see RC1 to AC ground. Remember that the supply voltage, all constant battery voltages become zero, become a short circuit. And then on this side also, I have R pi 2 to AC ground, or ground. So the total resistance that appears between the collector of Q1 and ground is RC1 in parallel with R pi 2. They are in parallel because they share these terminals and they share these terminals. So that tells us that AV1 is equal to minus GM1 times RC1 in parallel with R pi 2. So that was easy. Given the knowledge that we have developed before in terms of gain, input impedance, output impedance, everything else, it's not that hard to find the voltage gain of this stage while it is driving the second stage, while it is loaded by the second stage, right? This R pi 2 is loading the first stage and reducing its gain. The gain of the first stage used to be minus GM1 RC1 before we attached the second stage to it. But after we did, the gain dropped because this result is less than RC1. Okay, we found AV1. How about AV2? AV2 is the voltage gain from here to here, meaning V out over Vx. V out over Vx. How do we find V out over Vx? So in any circuit, anywhere in the world, if you're required to find V out over Vx, you are allowed to place an ideal small signal voltage source from X to ground, meaning that suddenly all of this disappears and you can say V out over Vx is that of this basic common emitter stage without anything, without any source impedance, without any load impedance. So AV2 is simply equal to, from here to here, just the gain of a common emitter stage. So that would be minus GM2 times RC2. All right? So now we multiply these two. That means, so this is our second observation here. And the third observation is that V out over V in, the total voltage gain, is the product of these two. The minuses go away. So we have one inversion here, another inversion here. They cancel each other. We have no inversion. So we have GM1 times RC1 in parallel with R pi 2 times GM2 RC2. So that is the voltage gain of this cascade. And hopefully, the product of these two gains is greater than what one stage could give us. It depends on the design, but that's our hope. With proper choice of these different values, we can achieve a relatively high gain because we have the product of two numbers. All right, that's an example of cascaded stages. As we learn other amplifier topologies, you can mix and match. You can have one common emitter stage here and then something else here, or something else before the common emitter stage, etc. Many different possibilities, but that's the basic idea. All right, one last question before we leave, and for that I give you 90 seconds. So quiz. Find the gain if VA is less than infinity, meaning that the early voltage is not negligible. So see how fast you can find that. I'll give you 90 seconds. Okay, so what did you find? Well, again, we don't really have to draw the small signal models as long as we remember the previous results that we had. So the previous results said that if we want to include the output resistance of the device, meaning early voltage is not infinite, we can simply place RC in parallel with RO here. So I can do this to show you. This is for the case of VA is less than infinity, right? Okay. How about here? How do we deal with that? Well, let's just go ahead and add the output resistance of the transistors inside the schematic. And for that, I will use a different color to make it clearer. So let's use brown. Now, you can add RO1, the output resistance of Q1, here in this schematic or in this schematic. You can draw it in the original schematic, you can draw it in the small signal schematic. It's fine, it's not quite correct if you draw it here, but as long as you know what you're doing, as long as you have a clear picture of what the circuit is about in mind, then it's not a problem. So I can draw RO1 here. And by that, I mean I have a small signal model for Q1. And what I did is I took RO1 out of it and explicitly drew it here. That should not be confusing. So now what's inside Q1 does not have RO1 anymore. We just drew it outside. And for this guy, we draw RO2 here. I'm call it RO2. Okay, so let's see how our equations have to be revised now that these ROs are included. For the first stage, we use our general mantra. We said the voltage gain of a common emitter stage is equal to minus GM of the amplifying device times the total resistance tied between the collector and AC ground. Now we have RC1 in parallel with R pi 2 in parallel with RO1. They're all in parallel, you can see. So we can say that V out over V in is now equal to minus GM1 times RC1 in parallel with RO1 in parallel with R pi 2. So that is the gain from V in to Vx, right? That's what we call AV1. And then how about AV2? The gain from here to here, the gain from here to here. Well, this is a simple common emitter stage, but it must include RO2 because we are specifying that early effect is not negligible. So if it must include RO2, it must follow this equation, minus GM times RC in parallel with RO. So that would be times minus GM 2 times RC2 in parallel with RO2. And this is the voltage gain of the cascade, including the output impedance. All right, the moral of the story in this example is that we are building upon topologies and simple equations to reach a point where we can analyze more complex circuits with relative ease. We don't want to draw the small signal equivalent circuit of this entire topology every time unless we really have to. Here, given these understandings of cascaded stages, the concept of input impedance, the concept of gain of one stage as described here, all help us write the final result. In fact, sooner or later, we don't even need to draw any of this. By just looking at that circuit, we say the gain from here to here is minus GM1 times RC1 in parallel with RO1 in parallel with R pi 2. And the gain from here to here is minus GM2 times RC2 in parallel with RO2. Okay, these are the things that we need to build up in our mind. You have to become comfortable and proficient with them so that as the circuits become more and more complex, we can easily handle them. All right, let's go to the next topic, the problem of gain variation. So as we know, the gain of a simple common emitter stage is given by minus GM times, for example, this, right? If you want to include early effect and so on. All right, we also know that GM is equal to the collector bias current IC over VT. So let's write that here. So we have AV equals minus GM RC if the early voltage is infinity. Again, whether we make this approximation or not depends on what we're looking for. Sometimes just to see simple trends, to understand the basic concepts, we neglect it. That's our first reaction. Unless at some point we realize that that approximation was not very good. Okay, then this is equal to minus IC times RC times VT. Is this gain well defined? Is this gain reproducible? Meaning that if I build an amplifier, a basic common emitter amplifier, and I put it in a package, put it in a box, and give it to you, and you start using it. Use it today, use it tomorrow. I give you 10 of these amplifiers because you need 10 of them. So you have 10 different samples of the same amplifier, and use one of them here, one of them in Helsinki where it's really cold in winter, use one of them in Saudi Arabia where it's really hot in the summer. So will all of these different amplifiers have the same gain or not? Well, no. So this is what we call the problem of gain variation. And if the gain varies too much for a given application, then the circuit is useless. The people will not be able to incorporate it in their systems. So let's explore and see why the gain varies. So the first issue is variation with temperature and process. I have to tell you what that means, process, but we'll get there. All right, variation with temperature. Is that obvious? That's sort of obvious. IC, the collector current of the device, is given by IS X of VBE over VT. So if VBE is constant, magically, then still VT is a function of temperature and IS is a function of temperature. If you remember, IS was in proportional to the junction area. It was also proportional to Ni squared, and Ni squared itself is a function of temperature. So IC varies with temperature. You go to Helsinki, you go to Saudi Arabia, the gain changes. That's what we call temperature variation. Variation with temperature. Now, what do we mean by variation with process? Well, process means the fabrication, the manufacturing process. So if I give you 10 of these common emitter amplifiers, will all of them have the same gain, even at the same temperature? No, because this value RC, this resistor, however you build it, has some variability to it. If you buy discrete resistors, they have a tolerance of 5%, maybe 1%. If you build the resistors on a chip, on a microchip, then the variation is even more. So we cannot guarantee that RC is precisely what we want. So the process variation means manufacturing variability, for example, in RC. So we see that IC varies, RC varies. In fact, RC also varies with temperature, so they vary all over the place. This is what we call a problem of gain variation. Now there is yet another interesting variation in the gain that's neither due to the temperature nor due to the process. So the other variation is what we call variation with signal amplitude. Strange but true. If I give you an amplifier and you speak into the microphone softly, it has a certain gain. It takes the signal from the microphone, this microphone, amplifies it by a factor of 30. On the other hand, if you speak loudly, then the gain changes. The gain will not be 10, the gain will be something else. The gain will not be 20, it might be something else. Why? Why does the gain of an amplifier depend on the input signal level, input signal amplitude? So for that, we have to dig a little deeper and see what's going on. But it's a very important and very interesting concept. Okay, so let's go back to our good old amplifier, which we have built a number of times. Here's our microphone, a little battery, V0, RC, VCC, that's the battery voltage connected to the top of the resistor. And again, let's pick some examples. Suppose this is 750 millivolts, V0. That's the base emitter bias voltage. That gives us a collector current of 1 milliamp. For example, I choose RC to be 1 kilo ohm. Okay? And I will choose VCC to be 5 volts. Just as an example. And now we would like to see what happens when this microphone produces a small signal or a larger signal. So far we have always assumed small signal analysis, meaning that this signal creates only small changes in this current. But that need not be the case, and all sorts of interesting things happen. Okay, well, let's try to plot the base emitter voltage as a function of time while the microphone signal is coming in, and also the output voltage as a function of time. Remember that these are always very good because they show us both the bias level and the signal fluctuations. Okay, so here's what we have for the base emitter voltage as a function of time. So VBE. Without the signal, when this voltage is 0, we have 750 millivolts. So we have 750 millivolts here. And now the microphone signal comes in. And let's say the microphone signal is not that small. In particular, I will assume that the microphone signal is a sinusoid with an amplitude of 18 millivolts. There's a good reason for 18 millivolts, you will see shortly. All right, so 18 millivolts peak, 36 millivolts peak to peak. Now again, you should not compare 18 millivolts with 750 millivolts. That's not the right reference point. You should compare it with VT, 26 millivolts, as we will see in a second. All right, okay, so now let's go look at the output and see what we have there. So for the output, in the absence of a signal, how much DC level do we have? So there's no signal here. We have 750 millivolts from base to emitter. We have 1 milliamp of current in the collector. VCC is 5 volts. If you remember, the DC voltage at the collector is equal to VCC minus RCIC. VCC minus RCIC. RC is 1 kilo ohm, IC is 1 milliamp. There's a 1 volt drop from here to here. So in the absence of that, we have 4 volts. So here we have 4 volts in the absence of a signal. Okay, now what happens when the signal comes in? Well, the base emitter voltage used to be 750, but now with the signal it goes up to 750 plus 18 or 750 minus 18. What happens to the collector current during these excursions? Well, it's not that hard. We write IC is equal to IS x pub VBE over VT. VBE is how much up here? Is 750 plus 18. So I will write 750 divided by 26 Vt times x of 18 over 26. So far so good, right? Okay, so let's change the color of our pen and see now what happens. How much is IS x of 750 over 26? Well, that's the current that we have without a signal, when there's no signal, right? So this is 1 milliamp. How much is x of 18 over 26? Is 2. So that's why I chose 18. This is equal to 2. E to the power of 18 over 26 is 2. Okay, so let's take a step back and see what happened. The bias current was 1 milliamp. That 1 milliamp of current gave us a certain GM, and that gave us a certain gain, minus GMRC. So if we had small signals here, the gain would be GM calculated at 1 milliamp times RC. But now, when we go all the way up here, how much is the collector current? The collector current has reached 2 milliamps. So when the microphone signal raises this potential by 18 millivolts, the collector current goes from 1 milliamp to 2 milliamps. What does that say about the gain? The gain increases. The gain is different now. The gain has doubled. So this means as the microphone signal raises this potential significantly by 18 millivolts, the gain goes up significantly. So remember that there's an inversion. So the downswing here is large because the gain is increasing. Now, consider the other case. The microphone signal is negative, so the base emitter voltage starts from 750 and goes down by 18. So how much is the collector current here? Well, if this is minus 18, this is 1/2, so the collector current is 0.5 milliamps. When the collector current is 0.5 milliamps, the gain drops by a factor of 2 with respect to what we had here. With respect to what we had here. So now, when the input is going down and the output is going up, the gain is less. So the signal has a smaller excursion. And so on. So this is what we observe. So let me just summarize everything that we have discovered. At this point, IC is 0.5 milliamps. At this point, IC is 2 milliamps. And at the bias point, IC is 1 milliamp. So the GM of the transistor is not constant with time as the signal comes in. The GM has some amount and then it goes up because the collector current is going up so much and comes down. So the gain of the amplifier changes with the signal level. The gain of the amplifier is minus 38. Remember from our previous calculations? Here. Then it goes up to maybe a factor of 2, minus 76. And then it comes down to minus 38 divided by 2, minus 19. So the gain changes considerably as the base emitter voltage changes by plus minus 18 millivolts. And if we look at this closely, we see that this is a distorted sinusoid because here we took a perfect sinusoid and amplified the positive half cycles by a lesser amount than the negative half cycles. So we got a distorted waveform. We call this distortion or non-linearity. So we see that the output has a distortion. Sometimes we call it non-linearity. So interestingly, the voltage gain of a common emitter stage varies not just with environmental issues, including temperature and process and manufacturability, but also with the signal level that's coming in. The larger the signal excursion, the wider this current range will be, which means the more the gain changes. The gain will be some amount here, much more here, much less here. And that's a problem. So that means that if we want to minimize distortion in the signal, we have to make sure that when the signal comes in, it changes the collector current negligibly. It has to change it, of course. If the collector current doesn't change, this voltage doesn't change, we have no signal at the output. But the change has to be small. And that had been our assumption in the previous examples. All right, now we will look at a circuit, a variant of the common emitter topology that alleviates these problems to some extent. It doesn't completely remove them, but it helps us alleviate some of these problems. And that's what we call a common emitter stage with emitter degeneration. So let's start a new page and work on the common emitter stage. It's very similar to the amplifier that we have here. So let's talk about the CE stage with emitter degeneration. All right, so we start out with our simple common emitter stage. As usual, we have a resistor here, VCC up here. Then, of course, at the input, we have the microphone or the input signal and the battery and all those things. And I just don't draw those for simplicity. So V in, V out is still here. That was the definition of the common emitter stage, if you remember. So the input is applied to the base. The output is sensed at the collectors. So those still are there. But now in the emitter, we do something. We add a resistor here before we go to ground, RE. And this resistor does also some interesting things to the circuit. In particular, it helps us with those variations that we just talked about. All right, so we would like to analyze the circuit. And typically, in cases like this, we are looking for three quantities: the voltage gain, the input impedance, and the output impedance. So this opens up all sorts of interesting problems to solve. One little resistor that we added here suddenly makes the problem much more interesting and much more complex. So we just have to be patient, go through analysis step by step, and make no mistakes. All right, so the first question is, how much is AV? Well, this is not a topology that we have seen before. We can't really use the equation that we had before for the gain of a simple common emitter stage. There we said the gain was minus GM times the total resistance connected between the collector and AC ground. But in that case, there was no resistor here. This resistor was 0. So we can't use that directly here. We have to make some changes. So then maybe we'll just draw the small signal model, see what happens, right? We just have to write some equations. Let's do that. Here's the small signal model. Starting from the input, we go to the base of the device. So we have R pi with a voltage of V pi across it. Then we have GM V pi as the dependent current source. For now, we'll assume the early voltage is infinite, so we don't have to worry about RO. This is the input voltage source. This is the emitter goes to a resistor to ground, RE. And then there's a resistor here going to ground, RC. And then this is V out. All right. Now again, I am using V in here. It's a little abstract. What I really mean is there's a voltage source, an AC small signal voltage source connected between the base and ground. Okay, so if you're more comfortable, you draw it like that. Otherwise, we stay with this abbreviated form. Well, our objective is to find V out over V in, right? The gain. And what's not desirable is this V pi. We have to eliminate this V pi from our equations. All right, well, what do we do? Well, what we don't want to do is panic. We just have to look at the circuit for a while and see what we should do. Again, don't jump into the equations. Look at the circuit, try to become comfortable, become familiar with what's going on, so that when you write the equations are intelligent, and they're not just nodal equations or KVLs and KCLs. All right, let's start from the output node. What can I see at the output node? Well, we have a voltage V out from the output node with respect to ground. And we also happen to have a resistor connected from the output node to ground. So we can say that the voltage across this resistor is equal to V out, which means the current flowing through the resistor is equal to V out over RC. So I just applied Ohm's law here. Okay. Well, can I write the KCL at this node? I have only two currents, this current and that current. So let's write a KCL here. So we say KCL at output node will give us this current plus this current must be 0. So we have GM V pi plus V out over RC equals 0, which means V pi is equal to minus V out over GM RC. Very good. We found V pi. We don't have to worry about V pi anymore. Okay, what else can we do? Well, we can write all sorts of KVLs and KCLs. Let's write a KCL at this node. We have two currents from these branches and one more current from this branch. So the way I like to think about it is a current is coming down here, and current is coming down here. They add up to each other and they flow through RE. Okay, like two rivers coming this way, and they merge and they become one river. All right, how much is the current coming down R pi? Well, it's the voltage across R pi divided by R pi. V pi over R pi. So let's write that. So here's a KCL at the emitter node, right? So the current coming down R pi is V pi over R pi. All right, so 1 over R pi times V pi. How much is V pi? Well, we just found it. So why don't we just do it like this? V out over GMRC. That is the current coming down R pi. How much is the current coming down the dependent source? GM times V pi, and we know V pi. So plus GM V pi, which is minus V out over GM RC. And these two currents come down and flow through RE, right? So if these two currents add up and flow through RE, they generate a voltage across RE. So I will change my color because I want to make sure there's no confusion. And I will say this. That was the result of KCL at the emitter. And I'm going to multiply this by RE and call it a voltage drop on RE, because this is the current through RE. Okay? So one thing you notice is that I am reluctant to define new unknowns So I don't call this IRE or something. I just keep it as is. I just write a little text here. You can see that if you resist adding more and more unknowns, then eventually combining these is easier. Okay, so we found out that this current plus this current flow through RE and generate a voltage, which is given by this expression. Very good. Notice that this expression has only V out in it. It doesn't have V pi in it because we eliminated V pi. All right, now in the last step, we're going to write a KVL around this loop. So let's see how that goes. So if I run the KVL around here, this is how I think about it. I say there's a voltage here, which I know. There's a voltage here, which I know. This voltage plus this voltage must be equal to this voltage. Now, if that's confusing, again, you can always draw this guy explicitly so that you can see it better, right? You can see, V in, because it goes from here to ground, is equal to V pi plus this, because it also goes to ground. So this plus this is equal to V in. So let's write that, KVL. So we have a KVL in input loop. And this input loop is not standard terminology. We just call it input loop because that's sort of the input, right? So if I write a KVL, this is what I get. I have V in is equal to this voltage, which is V pi. And V pi is this value. So minus V out over GMRC plus the voltage across RE. And that's this big monster here. So minus V out over GM R pi RC times RE. So I brought this in here and merged these. And then I bring this in here. So minus V out RE over RC, because this GM and this GM crossed. So congratulations. We have found one equation in terms of V out and V in. So now we can find V out over V in. So you see that as we write these equations, we are mindful of defining lots of new unknowns because they just make the algebra lengthier and lengthier. If we take our time and we are careful, we resist the temptation of defining, all right, I'll call this V something, V1, I'll call this I1 or something. It just gets more and more complex. So we keep track of the math carefully. Okay, one quick note. Is this weird that this GM crosses with this GM? What was this? This was GM times V pi. And it just happens to be equal to minus V out over RC. Is that strange? That's not strange. If V out over RC is this current, then minus V out over RC is this current, which happens to go all the way to here. So this current is actually the same as negative of this current. So that's not strange. Well, now we just need to find V out over V in. Again, let's make some simplifications. Do we know what GM R pi is? Remember, R pi was equal to beta over GM. So GM R pi is equal to beta. So that's nice. Beta here. And now we can write this as beta GM RC as a common denominator. And then here, I have a negative sign, I'll keep it over here. Then this beta goes multiplied by V out. Then here we just have RE V out plus RE. Let's see, something is missing here. This is V out beta RC. Oh, okay, sorry. There's a GM that is carried over from here. So let me erase that and go back here. So we have beta GMRE V out. That's for this guy. And then finally here, we have beta GM times RE. So that's also plus beta GM RE V out. Okay, I made a little mistake here. What goes in the numerator here is just GM RE V out, not beta. So let me erase this beta here and go back. Okay. All right, so that's what we have. So then we just factor V out and invert, and this is what we get. We get V out over V in is equal to minus, we have beta GMRC. Beta GMRC in the numerator. And then the denominator, we have beta plus GMRE plus beta GMRE. So we have beta plus 1 GMRE. All right. So we have GMRE here, we have beta GMRE here, so that's beta plus 1 times GMRE, and then we have beta. So this is the equation for the voltage gain of this degenerated common emitter stage. We're hoping that this stage will be somewhat better in terms of gain variation than the original common emitter stage. All right, ordinarily we don't take this equation as is, we try to simplify it, given reasonable assumptions. One assumption that we are pretty sure about is that beta is quite high, 50, 100, 200 or something. So it's a good approximation to assume that beta plus 1 and beta are close to each other. So let's go ahead and multiply the numerator and the denominator by beta GM. So that will give us minus RC. This will become 1 over GM, and this will become beta plus 1 over beta RE. And beta plus 1 over beta is close to 1, so that's approximately equal to minus RC over 1 over GM plus RE. That is the voltage gain of a common emitter stage with emitter degeneration. Our first reaction should be to see if this result gives us a familiar equation when RE is 0. When RE is 0, when we have no degeneration here, we get minus GMRC. Of course, that's correct. So no problem there. But now we see some interesting effects given by this equation. All right, so what does this tell us? This equation says if RE is large enough, then even though GM, which is IC over VT, changes with temperature, it affects this fraction to a lesser extent. Compare this with AV equals minus GM RC. So this is no degeneration, right? So we see that here, if GM changes by 50%, the gain changes by 50%, no question. But in this case, if GM changes by 50%, because we are adding it to some other number, the result will not change by as much as 50%. So RE tends to swamp the variations in this GM. So that's one interesting effect. So if, for example, the temperature causes the bias current to change, and hence GM to change, overall this result is not as sensitive as this result. The other issue is the variation of the resistances. Remember I said if you buy RC 100 resistors for RC, well, they have some variation. But what's interesting in this case is that if, especially for fabrication on a chip, what happens is that the resistors, all of the resistors on a chip, go up together or go down together. It's not like some of them go up, some of them go down from today's fabrication to tomorrow's fabrication. So because the resistors tend to go in the same direction, if this RC goes up and this RE goes up, this result doesn't go up as much as what we had here. So in terms of process variability, also this result is less sensitive than this result. So there are also some interesting effects that the common emitter stage with degeneration gives us that we did not have in the case of the simple common emitter stage. All right, we will continue to look at the stage in the next few lectures. It has many other interesting effects that come out of it that have repercussions in everything else that we studied. So it's not just the gain that has this little RE in there. There are other things. So we'll get to those in the next lecture. I will see you next time.